Hello class, and welcome to the second lecture on the section Project Initiation, where we look at how projects are initiated, how they are assessed, and how we decide if a project is worth going ahead or not, and also what constraints in terms of time, cost, and quality need to be applied to the project to keep the stakeholders happy. Now, today we're going to be looking at feasibility studies. Now, a feasibility study is basically a study into a potential piece of civil engineering infrastructure to see if we should go ahead with it, should we build it or not. Now, I think a very important thing to know is with the word feasibility, we often have the view, is it possible? Is it a study to see if the civil engineering project is possible? Well, that's not what a feasibility study actually entails, because anything is possible. We could send men to the moon, that's possible. We could build a ladder to the moon. Theoretically, it is possible. What we're trying to determine, though, is it viable? Meaning, are there enough stakeholders who are willing and able to take on the project? Another way of putting it is, do the benefits outweigh the costs? Meaning, is there a net benefit? And if there is a net benefit, then potentially the project should go ahead. If there is a net cost and there's more negatives than positives, then you shouldn't go ahead ever. Now, when weighing up benefits and costs, we can naturally weigh up the internal benefits, such as profit, and the internal costs, such as the money we have to pay to build it. However, when doing a feasibility study, especially for civil engineering projects, we are trying to do a cost-benefit analysis that includes externalities. We need to include external benefits and external costs in this analysis. Now, this is a real big challenge because often externalities do not have a value associated with them. So let's say, for example, there is a factory that is being built on the Zab River, next to the Zab River, and it can be built in a cheap way where its waste will pollute the Zab River, or it can be built in an expensive way where the waste does not pollute the Zab River. How do you put a value on that externality, meaning the external benefit of keeping the Zab River pure? Well, there's a few ways we can do that, and we'll talk about that, but it all comes down to consulting with the stakeholders, talking with as many of the stakeholders as we can and as deeply as possible. That makes a big effort that's a big effort for us, involved in valuing and putting a dollar value on all externalities, both positive externalities, external benefits, and negative externalities, external costs. Now, I've more or less stated this, but most feasibility studies center around this idea of doing a cost-benefit analysis, where we are trying to quantify the value of the project in terms of a dollar figure. Now, just because a feasibility study, a cost-benefit analysis, comes out positive, meaning there is a net benefit, that doesn't mean we should necessarily go ahead with the project, because the feasibility studies are usually combined in an options report, which I talked about in week 1, where we're looking at different options for solving a problem. Do we build a bridge over the Ainkawa Road, 100-metre road intersection? Do we build a tunnel? Do we just try to build a roundabout? Or do we just try to improve the traffic signals that we already have there? An options report will look at the different options by doing a cost-benefit analysis for each one and by determining which one has the best net benefit, and that's the option you should go with. So, this is a very, very famous feasibility study that was done for the rotating building of Dubai. Now, what you can see here is it's not actually 5 skyscrapers, it's just one skyscraper. And what is special about the skyscraper was that you can buy an apartment on each floor and they will rotate. You'll have a remote controller and you can rotate it and you can turn it and it can spin 360 degrees, so you can get views of every angle of Dubai. That was the thinking. Now, the civil engineering that is involved in building a skyscraper is colossal. The structural engineering is big, but the idea of having a rotating building, well, quite frankly, that just scares me. I just think the civil engineering requirements and the design risks are just huge. But anyway, they thought, let's see if this is possible and if this is viable. And before long, they realized it is possible. It requires a heck of a lot of engineering. It's really expensive, and the mechanical engineering is huge, but it is possible. Then they started to look into whether it was viable, meaning did the benefits outweigh the costs? And the costs were huge in terms of engineering, in terms of the design work, structural strength. Costs were huge. And that meant in order to sell each apartment would be roughly about 10 times the price of an equivalent non-rotating apartment in Dubai. And they then did a little bit of a survey of potential buyers, and they quickly realized that they were not going to be able to sell all of the apartments. There were not enough people who were willing and able to pay for an apartment that is 10 times the price of a regular apartment. There were plenty of people who were able, because there's a lot of rich people in Dubai, but there weren't enough people who were willing, meaning that they saw the benefits of having their apartment spin around. They didn't see the big deal. And so from this feasibility study, the Amar Development Company, they decided we're not going ahead with it, and they scrapped this project for the time being anyway. Now, they did this feasibility study. Now, you could say they were failures because they said, look, we're going to build a tower, and then they didn't. But actually, they are very happy with the outcome of the feasibility study. Can you imagine what would have happened if they had built this building and it was a white elephant, meaning that no one actually bought the apartments, and it just turned into a huge, huge money waster for the company? The feasibility study saved them from that. Now, that sort of feasibility study is quite simple because most of the benefits and the costs are internal. They are felt by the developer. However, with most civil engineering projects, they are public infrastructure, and there's a lot of external benefit and external cost. Look at the motorway at the bottom of that skyscraper. That is just as big a project as the skyscraper, but there is far more in the way of external benefit and external cost. Just look at all of those people driving on the road. They are all external beneficiaries of that road. So in order to do a good feasibility study, the the basis of a good feasibility study is nearly always a cost benefit analysis. And it's a very common term. You will probably hear the word CBA a lot, the acronym. What you're trying to do is you're trying to weigh all of the costs, so add them all up, and then also weigh all of the benefits. Now, with cost, you do need to consider opportunity cost as well. Uh, Unless, of course, it's part of an options report. So if you're doing if you're trying to find what is the net benefit for three different options, you would then choose the option that has the highest net benefit. You don't need to consider the opportunity cost of forsaking one option for doing another. But if it's not part of an options report, you do need to consider opportunity cost. Where else? What would I be missing out on if I don't use this? If I do this project, what would I be missing out on, and the cost of that? But the big one is external benefits and external costs, and that is huge. Most of the benefit is and most of the cost for civil engineering projects are felt not by the person who pays for it, usually the government. It is felt by stakeholders who have not invested a dime into the project. And because of that, it's very hard to quantify. So I gave the example of pollution earlier. Let's try another example here. Let's say that for electricity generation, the KRG decides they need to build a new generator. Now, they could build a new combined gas turbine similar to what they currently have, and it will cost them $100 million. And it will provide 1 gigawatt of power. Or they could build a new dam on the river. Now that's going to cost them a little bit more, probably $200 million, and it will provide 1 gigawatt of power. Well, there's more internal cost with the dam, but there's also the same internal benefit in terms of 1 gigawatt of power. But what you need to consider is the externalities. If you build the dam rather than building the gas turbine, you are going to have an external benefit of not polluting the atmosphere. Now, there's been a lot of study on this, but because of climate change, there's been a lot of study to try and quantify what is the net effect of climate change or greenhouse gases in terms of the economy. And what they are saying is that for every ton of CO2 you put in the atmosphere, it is costing the world, maybe not yourself, but someone, it's costing everyone about 20 to 30 US dollars per metric ton of CO2 that you put into the atmosphere. And that could be all number of things. It could be that it causes a flood in a different part of the world, which damages someone's property. It could cause a drought in Africa, which means a farmer has less crop. It could mean that a paint job on someone's car deteriorates faster because the sun is more intense and they need to repaint their car. It all adds up, the studies are showing, to about 20 to 30 US dollars per metric ton of CO2. Now, they have studied to quantify that externality. And that's a real challenge because normally externalities do not have a natural dollar value associated with them. And that's why we did those studies in our projects in engineering economics into the externalities of health and safety and also the environment. There is not naturally a dollar value associated with those externalities, and we need to find ways to quantify them and to put a dollar value on the externalities in order to do an effective cost benefit analysis. Now, we will talk about a few different methods. I think I'm going to show you 4 different methods of doing a cost benefit analysis. But first off, we need to look into ways we can quantify externalities. So, quantifying externalities. This is a really hard thing to do. And if you want to know more about this, you can talk with Avan, because this is actually much of what her 4th year project is. She's trying to quantify the external benefits and costs of compressed earth blocks. And it's a real challenge. But there is a few different ways that you can go about this. So one example would be the contingent value, which means how much will it cost to fix. So let's say we are building a road. Now we've got 2 options. We could build the road surface using asphalt, and we could build the road surface for $1 million. Or we can build the road surface out of concrete. There's a few concrete roads around. There's one outside Nair City where I live. Now that's going to cost a bit more. That's going to cost $1.5 million. So you would think, well, based on the costs, you'd go with asphalt. Well, not exactly. Asphalt deteriorates faster. Now, that means it will cost more to maintain. Is that an external? Well, yes, it is, in the case that usually for government property, there will be one department which is in charge of building infrastructure and another department in charge of maintaining infrastructure. So in a sense, it is an external. So if it's going to cost $100,000 to maintain the road every year, that is an contingent value. That is the external value. The next thing we need to look at is how much are people willing to pay. This is another way of quantifying externalities. So, what is the external benefit of having a building that rotates so you get 360-degree views? Well, this is done by basically surveying potential buyers and sellers and people who would be living in there, and basically asking them, how much would you be willing to pay for something as novel as a spinning building? And it's very hard to do. You've got to be very careful with doing your survey when you ask someone, because you've got to make sure people are willing. Remember what we said in engineering economics. To demand something, you've got to be willing, and you've also got to be able. So make sure that most people are willing to live in a rotating building. It would be pretty cool, but not many people will be able. So the question is, will people demand it? Are they willing and are they able? Now, with a spinning building, you've got to do something like a survey of potential buyers of apartments. But with a lot of projects where they're not so novel, you can look at the externalities which were realized with similar projects. So if we're building a motorway, for example, and we know there are externalities such as what the the cost to the neighbours having the noise pollution, and the cost in maintenance to the asset management people and the government, the cost of to families when people die on the road because you didn't build the motorway in a safe manner. These externalities have been realised with other motorways, and you can basically quantify an externality and put a value on that externality by what was realized with previous projects. That is why most projects now, in the developed world at least, have a very high standard of health and safety regulation. They're trying to internalize the externalities by having regulation on health and safety. Now, that came about basically because for many decades there were lots of people dying on project sites. The the Hoover Dam, for example, 200 people died there. And they realized after those projects had happened, there was a huge external cost to the families. Often there's a big bit of research now showing that children who grow up without a father because he died in a work-related accident, they are far more likely to be in poverty. They are far more likely to flunk out of school. They're far more likely to commit crimes and end up in prison. There's all sorts of butterfly effects that cause an external cost to a society when someone dies on a project site. Now, we can quantify those externalities for our project by looking at similar projects. So we can, if we're building a dam, we can look at previous dams and look at what was the value of their externalities in terms of the environment, in terms of real estate that was lost, in terms of people dying on site. You can measure all of those external costs and benefits and then apply it to your project. Now, one external benefit which is always overlooked, it seems, is the GDP stimulus or fiscal stimulus. What do we mean by that? Well, you can talk to an economist or someone in marketing or finance, and they will talk about this. That when there is a big project, a big civil engineering project, one of the external benefits is that it creates a lot of stimulus in the economy. It creates jobs. Those jobs will mean that there will be more people who will have income. That will mean that they will spend more, they will buy more things, which means that businesses will do better, which means businesses can expand, which means businesses can sell their products elsewhere. It stimulates the economy. Now, remember the Hoover Dam example I showed you in engineering economics? That is a huge dam that produces 2 gigawatts of energy, of electricity, and they built it in the 1930s. Now, there was no way anyone needed 2 gigawatts of energy back in the 1930s. That's a huge amount of energy. Until the 1960s, they weren't even using the Hoover Dam to its full capacity. Why did they build it then? Well, President Hoover understood what externalities were, and he realized there was an external benefit of GDP stimulus. It created over 6,000 jobs in a time when jobs were sorely needed. It was during the Great Depression. It kept thousands of people out of poverty. And so he considered that external benefit, and he judged in the feasibility study, yes, we should build this dam. Even though we don't have a use for the electricity at the moment, we should build it. So that's another way, that's just one external benefit that you should take into consideration. And the great thing is that there are a lot of measures for measuring and quantifying GDP stimulus. Another way of quantifying an externality is restorative costs. So this means how much will it cost to return the environment or the land back to its original state. So how do we measure this? Let's go back to the example of a factory that is built beside a lake. And this factory is building concrete blocks, and it is creating a lot of cement leachate. This is water which is very polluted with cement particles. Now, they've got a choice. Do they dehydrate this and make it into a solid waste that can then be disposed of at the landfill? Very expensive. Or do they just dump the dirty water into the lake and kill all the fishes? Well, one way you can quantify the external cost of dumping the water into the lake is you can look at the restorative costs. Once this factory has polluted the lake, how much will it cost the society to clean the lake? How much will it cost to restore the lake, to remove all the cement from the lake? And those costs can be very high and give a very high external cost. The other way to quantify an external is to look at something called hedonic pricing, which means what is the savings in fuel or operating cost of the current infrastructure. So let's say that the government wants to build a wind turbine farm for generating electricity, a wind farm. Now, this wind farm will make 10 megawatts of power, let's say. Now, there's very big costs with renewable energy, so you've got to make sure you quantify your externalities well if you want to get your renewable energy project approved. One of the things that needs to be considered is the savings in fuel and operating cost of the current infrastructure. What do I mean by that? Well, if you have a wind farm that is producing 10 megawatts of power, that means the current gas generator can produce 10 megawatts less of power every day because the wind is going to make up the difference. That means that the government will save in fuel. They will save gas. So that savings is an external benefit. You need to consider that with all renewable energy projects. More so than that, you also need to consider that they can sell that gas that they're not using to generate electricity to the Turks, sell it to Turkey, get more money for it. That is an external benefit too. And it goes on and on. Now, quantifying externalities, just a final thing I want to say is that there are lots of different ways of quantifying externalities. And in a feasibility report, it's very important to explain how you're quantifying the externalities, why you think it's worth that, why you've placed that dollar value for each external. And you've also got to make a justification why you think it's the best way to quantify externalities. But I can tell you this is an art rather than an exact science, because basically you're trying to be a prophet. You're trying to predict what will be the external costs and benefits after a civil engineering project and infrastructure is completed. And so there's a lot of different variations in feasibility studies for this reason. So let's have an example here of trying to quantify the externalities. Again, we are going to look at the example of having a bridge going over the Ainkawa Road and 100 meter road intersection. What are some of the externalities there? Well, one of the basically nearly all of the costs and benefits for motorways are external because they're usually felt by the drivers themselves who don't pay directly for the road, unless of course it's a toll road. But there's an external benefit for those who live in Ainkawa. When they go into work every day in the city and they come home, they can spend maybe 10 minutes less on the road. That means they can potentially have 10 more minutes at work where they can work harder and they can produce more. It stimulates the economy. It means they can spend more time with their family, which means their kids will probably do better at school, which means in turn they will stimulate the economy further. There's the externality of this bridge probably employing maybe 500 people in the construction of it. That means that for several months, 500 families will have bread on the table. There won't be as much poverty in Erbil as there would have been if they hadn't built this project. What about the external benefit of the car that is driving from Ainkawa and wants to go to the airport entrance and turn right and use that right-hand turn? Well, the benefit to him is probably that there's going to be less traffic. He doesn't have to wait for a traffic signal as he currently does, so he has more time. And you go forth and you use the principles of quantifying externals to put a dollar value on all of these external benefits and costs. Now, I will say that with a motorway project, one of the major things you should do in a feasibility analysis is do a traffic survey. Find out what percentage of cars are driving through, what percentage of cars are turning right from this road to that road, what percentage of them want to turn left, what percentage of them are currently using the U-turn further up the road, and so on and so on. That way you can quantify the external benefits. If you have a dollar value for every car that uses the intersection, you can quantify what is the external benefit and cost for each feature of this project. So now let's say we have assessed what is the a value for the external benefits and the external costs. Now we need to assess everything using a cost-benefit analysis method. Now, the cost-benefit analysis method that I'm going to tell you first is a net present value method, or NPV. Now, one thing that you need to realize is that external benefits for civil engineering projects can be felt for many years into the future. In fact, many of the stakeholders are future generations who don't even live yet. We talked about this, about how civil engineering projects, the infrastructure can last 100 years or more. And so you need to consider the benefit for all of the years in the future. But there is an issue. A benefit in the future is not the same as a benefit now. Now, this is explained in an English expression: a bird in the hand is worth two in the bush, meaning most people would rather have the ownership of one bird then the opportunity to potentially have two birds if they go hunting in the next year or two. That makes sense. Another way to put it, if I gave you a choice of, let's say I wanted to be really nice to you, and I say, here's $10. I want to give you $10, 10 US dollars, and I just give it to you with no strings attached, no cost. I just give it to you as a gift. Or I say, I will give you $11 in 2 years' time. Well, what are you going to choose? Will you choose $10 right now or $11 in 2 years' time? Well, I suspect most of you will actually choose the $10 right now. Even though $11 is more than $10, you will realize that benefit and know the benefit right now. If I promised you $11 in 2 years' time, there's no telling what could happen in 2 years. I could die in 2 years. I could leave the country. I may try and swindle my way out of the deal. And so a net present value method is a way of trying to consider what is the value of a benefit that will be realized tomorrow and giving it a value for today. And this is where discount rates come in. I don't know if you've ever heard of this term discount rates before, but it doesn't mean like a discount or a special or a sale at the supermarket. A discount rate is an economic rate by which or ratio by which we assess economies or marketplaces to see how willing people are to wait for a benefit. And you don't need to assess discount rates. Normally they are already given by chambers of commerce. There's economists who assess these rates, and I'm not going to go into how they do that. But let's just say that the discount rate in New Zealand currently is about 5%, meaning that if I was given the choice of having $100 given to me today or $105 given to me in a year's time, or sorry, let's up the ante, $100,000 today or $105,000 in a year's time. There's been a lot of assessment to say that that is the cutoff. 50% of the population will say, let's wait 1 year to get an extra 5,000, and 50% will say, give me 100,000 right now. Now, in Herbal, the discount rate, I understand, it's actually very high. It's around 10-15%, meaning that people are not very patient here. They do not want to wait to realize the benefits of their project or business. And the reason for that is because there's a very temporary mindset here. It's a very unstable country. I think even in my lifetime there's been about 4 wars in this part of the world, maybe even more. And so people do not want to invest in any sort of project that will give them profit or benefit in 20 years' time, because they think, you know what, the country could be destroyed by then. Who's to say that someone isn't going to bomb the bridge or the building within 20 years' time? And therefore there's a very short-term mindset in this country. And that's not a criticism, that's just a reality. Meaning that a benefit tomorrow is not worth as much as a benefit tomorrow in a country such as New Zealand, where people have a bit more patience for benefit in the future. And therefore the discount rate is much higher here, it's about 10%. Now, hopefully that makes sense to you. I will send you something about discount rates and give, if this is unclear to you, I will put something on Moodle about that. But let's now look at an example. So this is an this is the net present value method. Basically, you are trying to determine what is the net benefit of the net present value of a project. So, capital cost, that is the amount of money that you have to spend to build the bridge or to build the road or to build the dam. Now, the net benefit is the benefits minus the cost. Now, that includes externals as well as internals, and that's going to be realized every year. Now, R is the discount rate, and that will depend on where the market is, whether it's in Erbil, whether it's in Baghdad, whether it's in Egypt or wherever. There is a different discount rate that is associated with different markets. So what we're trying to do here to find the net present value is we're trying to add the net benefit from every year to, and it's been adjusted to the discount rate. We take the sum of the net benefit from every year that the project infrastructure will be open, and we add it to the negative value of the capital cost. So that is that equation right there. Now, I'll try and show you how that is. Just a word of warning, that x by the b there, that is not an exponential. It's not a power. That's just to mark that it's the net benefit from year x. So let's look at an example here to see that equation in practice. So let's say we're building the Ainkawa Bridge. It's going to cost $10 million to build. I can assure you building a bridge like that will cost much closer to 50 million. But anyway, the annual net benefit, that's benefit minus cost, including externals, is expected to be $400,000. That's in savings from traffic jams, GDP stimulus, all sorts of external benefits and costs. They come down to being $400,000 a year. That's what you're experiencing. Now, the bridge is expected to last 30 years. Again, a bridge should probably last much longer than 30 years, but anyway. And in this example, the discount rate for Erbil, it's given. Remember, we're trying to teach you to be an engineer, not an economist. So you will always be given the discount rate if you're doing this. So don't worry about exactly how we came to the 5%. Is the bridge worthwhile doing? How do we do that? Well, look at the inputs there, and now let's plug them into the equation. The net present value is the negative capital cost, so that's $10 million, so that's the negative 10 million there, plus $400,000 over 1.05 to the power of 1. That is the benefit in year 1, plus 400,000 over 1.05 to the power of 2. That is the benefit adjusted for today from year 2. And we go all the way up to year 30, which is $400,000 over 1.05 to the power of 30. Now, we can plug that into our calculators. It's actually, I personally think it's a lot easier to do with Excel, but the value will come to being negative $3.85 million. That is the value. So, Should we be doing the project? Well, no. It would be better if we did nothing at all. The net present value of this project is not enough. It's no good. Now let's look at another method, the rate of return method, and the inverse of that, which is called the payback period. Now, for those of you who have ever looked into business or investments, this method might be a little bit more similar for you than the net present value method. But the rate of return method looks at the average percentage of annual return over the overall cost. And remember, those costs include externals when we're doing civil engineering projects and a feasibility study. And once you have the percentage, meaning what is your percentage benefit every year, you can then compare it with other solutions, other investments. Now, if it's a very high risk project, you need to have a higher rate of return. So I can make 5% in interest by having money in a bank account in New Zealand. So I have $100 in a bank account, and I go back in a year's time, it's now $105. Now, I could also invest in building a business here in Erbil. And so I spent $10,000 to build a pizza restaurant, let's say, and the return rate that I'm predicting is 5%. That means I will have I would have made $500 by the end of the year. Am I going to do that, or am I just going to put money in the bank in New Zealand? I'm going to put money in the bank in New Zealand. Why? Because there's way more risk associated with opening a business here in Erbil. What happens if someone gets sick? What happens if some of my calculations are misjudged? What happens if I get kicked out of the country? There's a big risk I could lose all of my money, and therefore to be willing and able and to be willing to invest in such a higher risk project, I want a higher return. Now, the payback period is basically the inverse of the rate of return, meaning it's trying to determine how many years before you make the money that you put into the business. And it's basically the inverse of the rate of return. So if the rate of return is 5%, then the payback period will be 1 over 0.05, which means 20 years. And for a project to have any chance of being viable and being feasible, the payback period must be less than the lifespan of the infrastructure in civil engineering. So if the payback period for the bridge is going to be, for the dam, let's say, is going to be 40 years, but the dam itself is only going to last 30 years, you would not build the dam. So here's an example of the rate of return and the payback period method. And we're looking at exactly the same example, the Ainkawa Bridge again. It's going to cost $10 million to build. The annual net benefit minus cost each year is expected to be $400,000. And the bridge is expected to last 30 years. And you need to use the rate of return method now to determine if the bridge is worthwhile building. So let's look at this. The rate of return method is basically looking at the benefit or profit you would be making every year as a proportion to what you put into it. So 400,000 over 10 million. That is 4%. The payback period is 1 divided by 0.04. Sorry, I'm missing a zero there. That should be 0.04, not 0.4, which will come to being 25 years, meaning it will take 25 years to realize all the net benefit, a total cumulative net benefit of $10 million. It will take 25 years, external benefits and internal benefits. So that's less than 30 years, which is the lifespan of the Ainkawa Bridge. So that's the first test. So my question is it worthwhile building this bridge? Well, that will depend. If it's a 4% gain in benefit every year, maybe you can get that 4% with a lower risk project. If you were going to look at all of the drivers who were going to make an external benefit of, say, $20 from the bridge every year, each driver made an external benefit equivalent to $20 every year, and they said, and you said, do you want us to build this bridge that you can use, or do you want us to just give you $20 and carry on with the current intersection how it is? Potentially, a lot of them will just take the $20 because of risk. Potentially, the bridge isn't going to live up to the grand goals that it set out to. So the rate of return for a civil engineering project, which is a very high risk project, you normally want a rate of return, I would say, of around 30%. But of course, basically to assess whether it's if it should be done or not, you've got to look at different options. Is it really an option that you could give that $20 to every driver and let them deal with the bad intersection? That's probably not an option. But you could look at the different options in your options report and do a rate of return assessment for each one, and then you can compare. The final method that I want to talk about is the levelized cost method. This method, it seeks to determine the overall cost for a single unit of benefit produced. That sounds like a big mouthful, but this is usually used for infrastructure that has a production output. So they do use it occasionally for motorway projects where the output is number of cars that bypass a city, for example, but it's often used for factories, building a factory that will be producing Coke bottles, or it will be producing concrete blocks, or it will be producing ceramic tiles, or so forth. Now, one of the most common uses for levelized cost method is something that I've done a lot of because I worked in the electricity industry, is to try and find the levelized cost of energy. That means we are trying to measure how much it costs to produce every kilowatt hour of energy. A kilowatt hour is a measure of energy. And we call this the LCOE, the levelized cost of energy. Now, generally, with a standard levelized cost method, you are not considering externals. And that's a problem in civil engineering because most of the costs and benefits are external. So you need to value the externalities, which we talked about, and then you need to adjust the levelized cost method. So this is called the adjusted levelized cost method. So let's look at an example of this. This is an assessment, an example to see if the university should build solar panels on top of the roof. of the campus. The university currently pays $0.06 or 6 cents per kilowatt hour of electricity. So that's combined with electricity fees and also diesel for the generator. Now, the Vice Chancellor, he thinks it might be a good idea to build solar panels on the roof. By the way, we no longer have a Vice Chancellor. The new guy in charge is called the University President. Sorry, I should update that title. But to build the solar panels on the roof, the capital cost, the cost we'll have to pay up front, it will be $15,000. And in terms of maintenance, just maintaining the solar panels, we're going to spend an extra $500 a year. Now, the solar panels, they're going to produce 20,000 kilowatt hours every year. That's how much energy they will produce. And they should last for 10 years. Well, should we buy them? Well, one way of doing this is to look at the levelized cost of energy. So let's have a look here. The total life cost will be $15,000. That's the capital cost we pay up front, plus $500 in maintenance every year for 10 years. The total life cost will be $20,000. Now, the total amount of energy that it will produce in its lifetime, when we're talking about the solar panels, will be 20,000 kilowatt hours every year for 10 years. So it's going to produce in its lifetime 200,000 kilowatt hours. Now, the levelized cost will be 20,000 over 200,000. That's going to provide a dollar value per kilowatt hour. And that comes to that we would be spending $0.1 or 10 cents per kilowatt hour. So the question is, should we build the solar panels? Well, if we were going to just do a plain levelized cost method, we would then take that 10 cents per kilowatt hour and we would compare it with the standard, what we currently use, using gas electricity from the mains and also the diesel generator. And we would compare it with the $0.06 per kilowatt hour or 6 cents per kilowatt hour that we are currently paying. And we would say, no, we shouldn't do this. The levelized cost of solar panels is higher than if we just use the diesel generator. We shouldn't do it. However, there is a question though here. If the Vice Chancellor or the University President, he's only thinking here about internal benefits and costs. If we're good civil engineers, we should be thinking about external benefits and costs as well. So there's going to be an external benefit about just us feeling good about having renewable energy on our roof. What happens if the solar panel is the difference between one more student saying, I don't want to study at Chihan University, I want to study at UKH because I like their solar panels. That's an extra $5,000 in tuition fees every year for 4 years. So that's a benefit that you need to account for. There's also the external benefits of improving the environment, of not releasing greenhouse gases. There's also the external benefit of not having a noisy diesel generator, which affects learning, and it also creates more room. It gives us more real estate because the diesel generator takes up a lot of room. That could be another classroom. So you've got to look at all of those external benefits and costs and make an adjusted levelized cost when considering renewable energy. And usually when you start doing that, suddenly renewable energy looks a bit more viable and feasible. So here's an example of different levelized costs of energy, and these are being measured in cents per kilowatt hour if you look down at the x-axis there. And on the y-axis, we've got different ways to generate electricity. So we've got hydroelectric from a dam, we've got coal, we've got gas, wind, solar power, all sorts of ways of making electricity. And the question here is, what is the levelized cost of energy for each of these? Well, first off, you can see that there is a huge range. You can see there's big bars, especially for something like solar photovoltaic. Why is that? Well, the levelized cost of energy will be very proportional to the weather. If it's a very sunny place, then the levelized cost of energy will be a lot lower. If it's cloudy, then it'll be higher because you're not going to generate as much electricity. A solar panel look at it this way. A solar panel in New Zealand, which is a very cloudy country, costs just as much money as a solar panel in Australia, which is a very sunny country. Now, the solar panel in Australia will generate more electricity, but the cost of the solar panel is the same, and therefore the levelized cost of energy for solar photovoltaic in Australia is much lower than it is in New Zealand. But you can see that solar doesn't do very well. Generally, the levelized cost of energy is very high. Wind as well is quite high. You're looking normally around 20 cents per kilowatt hour. Compare that with gas or coal. Well, the levelized cost of energy is closer to 10 cents per kilowatt hour. So you can sort of see why economically governments are often not that keen to invest in renewable energy, because the sums, when you look at the levelized cost of energy, just don't add up. Now, the reason for that is because generally with renewable energy, the capital cost, that initial outlay of cash, is very high. Look at hydroelectric, which is one of the better ones for levelized cost of energy. That can to build a dam, you can't really build any kind of dam these days for under $1 billion. A dam of any reputable size that will give you at least 20-30 megawatts of power. You have to spend at least $1 billion. And most governments are just not willing to spend that. They will rather just run more coal or more gas through their fossil fuel generator that they currently have. Now, another thing to look at here is look at wind onshore and wind offshore. So we're looking at two different kinds of wind turbine farms. One is built on land and one is built out in the ocean. And you can see that the levelized cost of energy for wind built on land is a lot lower. It starts at 5 cents a kilowatt hour, whereas wind offshore starts at 12.5 cents per kilowatt hour. Why then would anyone ever consider building a wind farm offshore? Most of the wind farms in Europe are built offshore. Why do they do that when the levelized cost is much lower? Well, it's because of externals. There is an external cost to building wind farms on land, and that means you lose land. That could be used for real estate, for farming, for development, for motorways. You can no longer use it. Building the wind farm offshore, there's a lower external cost in terms of missing out on what that land could be used for. And so, as I say, levelized cost of energy, it really does change the landscape, and it really improves the feasibility and viability of renewable energy when you start valuing and including the external benefits. So that's all for that slide. So here's a question: should we build renewable energy in Kurdistan? If so, what should we be doing? Should we be building wind farms in Cham Chamal, which has the best wind in Kurdistan? Should we be building solar panels on the Erbil plains? Should we be growing biomass and long grass in places with good farming, such as Hiran and Shaklawa? Or should we be building another dam on the Greater Zab River or the Lesser Zab River? Well, that would make a very good options report, wouldn't it? Where you could do a levelized cost, a net present value, and a rate of return for all of these different options and compare it with the current status quo. And you would need to look at the external benefits and costs of each one. That would make a very good research project for anyone who wants to do a master's. Hint, hint. So, supplementary reading, if any of this is unclear, particularly around the net present value, the rate of return method, the payback period, and the levelized cost, you can read about this in Panesh Selvarm's Engineering Economics, pages 51 to 63 and pages 97 to 108. And there's a little bit in there about feasibility studies as well. There's also a chapter on feasibility studies and cost-benefit analysis in the project management book by Abenlada, which is available as a PDF on the Moodle page. That is supplementary reading. You're not required to have any more in-depth knowledge than what I have shared with you in this lecture slide, but maybe that will help solidify and solidify your learning today. That's all I have for you. Thank you and goodbye.